a little bit about Chapter 7. What we have done so far is laid out the basics of what we describe as the SN2 reaction and the SN1 reaction. Obviously, next week's exam, a lot of this stuff is going to be there. And it can be quite tricky to decide what's going to happen when, so that's what we do today, is try and sort that out. But what I want to do first off is go back a little bit and look at the stereochemical situation in the SN1. Now, in the SN2, when the nucleophile comes in and it boots out the leaving group, that's always an inversion. You always get one chiral molecule going to another chiral molecule if you start with a chiral system. When you start with a chiral system for an SN1 reaction, it's different. Okay? For the SN2, if you start with a chiral system, the molecule will have an alpha D, measurable, and your product will have an alpha D, different but measurable. And you can say then that this is going to be an inversion process. With the SN1, I think it's more complicated because what you end up with is a system that doesn't have any alpha D. It's zero. And this is because of the fact that you get a carbocation, and that carbocation is flat. And for the systems you'll see with me, you're going to get a racemic mixture. You're going to get two products formed in equal amounts, and their optical rotations will cancel out. So that's shown on this, this chart here, this slide here, where the starting material collapses, and the leaving group breaks off, and we'll say the leaving group is not hanging around here. Okay, that's what the next slide will show you. And we now have equal access to this side and equal access to this side. Don't forget, absolutely fundamental, that a positive charge is an empty p orbital. And those p orbitals are symmetrical, so this side is the same as this side, and you can attack either one equally as well. So that will give you some of what we call inversion product, in which the nucleophile came in from this side, in other words, the opposite side to where the leaving group broke off. And you'll also get something of what we call the retention product, in which the nucleophile added from this side, same side as to where the bromine came off. It's all based on the fact that the carbocation is flat and equally accessible from both sides. So with that in mind, I left off with this slide, and this slide is always confusing. In reality, and obviously we have to deal with reality at some point, that leaving group hasn't just disappeared. It hasn't sort of disappeared to the other side of the universe. It is still there. So as it breaks off with its pair of electrons, it is still hanging around. And it's hanging around on this side of the system, not this side, because it broke off from this side. That means that this is going to have something to say about the approach of the nucleophile. It's going to get in the way to an extent. So we'll find that often in reality, and you should be able to explain this, we get a little bit more of the inversion product because the nucleophile has easier access from this side, and you get a little bit less of the retention product because the leaving group is still there. I'm going to set this up for the exam to give you clues. I'll tell you that the outcome of a process is a racemic mixture, or the alpha D equals 0. And from that, you should be able to infer, okay, it's an SN1 reaction, because in the SN2 reactions, I don't get that racemic mixture. And if it is an SN1 reaction, I must be dealing with a carbocation. So we're going to deal with this from different directions. Please have a look at the old exams. Don't memorize them. Try to understand this stuff so we can go further with it. So this is sort of reality, and then what we need to do is practice, and obviously in recitation for the next week, we want to do a lot of that. Office hours, again, some of you are starting to show up, which is good. If you're coming to see me next Thursday afternoon at 4 o'clock and it's the first time I've talked to you, then no, it's not going to work. Right? It's up to you to actually be responsible about this stuff. So we're looking at a system here which is tertiary. That's the first thing you look for, the criterion, to decide what type of reaction we're going to get. This is a tertiary alkyl halide in the presence of something like methanol. Now, you'll find that these types of SN1 reactions often involve something called a protic solvent. We'll deal with that today. The solvent is somewhat acidic. It has an acidic proton. And what that allows to happen is hydrogen bonding. So people have been asking me in office hours, how is it possible for that bromine to come off if it gives you an unstable cation? And the answer is the solvent will help it come off by hydrogen bonding. And if that's the case, you'll get a tertiary cation, and that's going to be flat, and it'll be attacked from both sides, and ultimately we'll end up with racemic mixtures. This is a very useful way of making different functional groups. You can see here, alkyl halide. What type of functional groups are these? What types of functional groups are in those products? That's an ether, right? If you don't remember this stuff, that's why we go downhill rapidly, right? If you don't remember these things, you need to. It's important. So we can see there a fairly simple synthesis. We can see on the left over here a little bit more stuff in there. It actually doesn't do anything. What you're looking for here is a tertiary system, which is chiral. And then when you bring in this material which has hydrogen bonding capabilities, it's going to allow for an SN1 reaction. Why not an SN2 on this carbon? It's too crowded. It's way too crowded, so the SN1 takes over and we go in that pathway instead. And again, we get this racemic mixture in which the OH group came in from one of either side. Fairly standard stuff. Down at the bottom, be very careful here. This has tripped some people up on their homeworks and on the quizzes. This starting material here isn't chiral. Even if I were to put something like this, a methyl group as a wedge and a methyl group as a dash, your first instinct is to say, okay, chiral system, therefore a racemic mixture. And the answer is no. Right? There isn't a chiral center in the starter material, so it doesn't matter which side of the carbocation you attack from, you're going to get the same thing, and that's going to give us an achiral product. Okay? Now, there's a bit more to this. You have a carbocation forming at this carbon. Do you think that benzene ring system has anything to say about that? If you put a plus charge next to a double bond, what can you do? Resonance. So resonance will be a key factor here. That will allow for SN1 reactions to happen. So look at the examples, put the two things together. This is what I did for about 7 people yesterday who came into the office, and I did this for about 5 minutes. I think it was useful. We set out the basics of the two reactions, and you must put them together to see the differences. If you're studying them sort of independently, that's not going to help. You need to see why tertiary systems go in one direction and not the other, and why primary systems go in the other direction and not the other. You need to compare the two. So this slide is useful because it shows you the comparisons. In the SN2 mechanism, if we add more nucleophile, it goes faster. If we add more electrophile, it goes faster. So it's a biomolecular process. It's only one step, and that involves the nucleophile kicking out the leaving group. The nucleophile has to approach from the opposite direction from which the leaving group is breaking off, because that's where the empty orbital is to dock with. So the nucleophile comes in, boots out the leaving group. Everything's happening at once, concerted process, and we'll say the right-hand side is more stable. The leaving group broke off and became a stable anion. So we'll need to worry about what this thing is at the top. Again, if you can draw those things, great. If not, find out how to do so. And we see now that we have an exothermic process and a very simple idea. It's actually completely analogous to the acid-base chemistry, and an acid-base chemistry is very much like an SN2. Down here, we can talk about rates of reaction. Methyl, the most accessible, is the fastest. And as we start adding stuff to the alpha carbon, things start to get slower. And they get to a point with the tertiary systems where they just won't do SN2 reactions because they're too crowded. The stereochemical idea here, inversion of configuration. It always happens with inversion, but you can only measure it if you start with a chiral system. On the right-hand side, the SN1, the steps are different, and that's really it. For the stuff you will see for this next exam, the different mechanisms are basically what happens when. They differ in the timing of the events. So on the left, both things happened at once. The nucleophile came in and the leaving group broke off. On the right, it's different. On the right, it's the leaving group breaking off first. So I can't do an SN2 over here because it's too crowded. So what tends to happen instead is the leaving group comes off and we produce a carbocation. And that carbocation now is stabilized by what, Haldeman? Hyperconjugation, which is? Wow, you remembered it after 2 days. I'm impressed. Okay, so yes, the more of those adjacent bonds you've got, the better. So a tertiary system is better than a secondary, is better than a primary. That needs some help. It does form. We can prove it forms. It needs some help from the nucleophile, whatever that happens to be, and we get a substitution product. Notice the products are similar here. We do get substitution products, but the graph is quite different. This is stepwise. There's step 1 and there's step 2. Now, which of these two steps is the rate determining, A or B? A. It's the higher barrier. Don't forget these barriers are the horizontal distances. So the first step is rate determining. That means the leaving group's breaking off. It will happen, and you'll realize now that the nucleophile is not needed till the second step. So even if you add more nucleophile to this, it won't go any faster. It's not part of the rate determining step. And opposite to what we had on the left, we can see down at the bottom that the tertiary system is fastest, and then secondary, and then primary and methyl. And you can start to say for certain primary systems and methyl systems won't do SN1. They can do SN2 instead, right? So you'll get this break in the middle, and the secondary systems are the problem. Michaela. Most reactions will. Yeah. Joe.
What if you have hydrogen bonding? Then will your rate determining step always be A?
The rate determining step in an SN1 reaction is always the formation of the carbocation. That isn't necessarily always step A. There might be something happening before that to set this up, but the rate determining step will always be carbocation formation. Okay? So I'm going to start talking about a bit more detail to fill this out and flesh it out and give you some idea of how this is useful. We have started talking so far about alkyl halides because they're very good leaving groups, but you can start to think about how to make those alkyl halides, and one way is to start off with an alcohol. Alcohols you can get from nature, okay? You can distill them from various sources, and so that's a good starter material. In fact, alcohols will be one of the most useful starter materials throughout the 2 semesters because we can get hold of them in bulk. Now, if we treat this material with HCl in acetic acid as a solvent, it turns out we get a chloride product, all right? So we can make these things. Now, if you read the statements at the bottom, the reaction requires the acid. It won't work if you don't have the acid. You'll see why in a second. And the rate determining step is unimolecular. Okay? You can measure that easily by adding more nucleophile. So how is this different? Well, it's going to be more complicated. Everything from now on is more complicated. So what I'm going to say here is that this isn't a very good leaving group. Why not? If that thing breaks off, what does it become? It becomes hydroxide, and hydroxide is unstable. Okay, so we need some help here. So hydroxide itself, at this stage, won't break off. We'll be able to do something else in a preliminary sense to help it break off. So let's think about this conceptually. This is a stable molecule, and this is not. And the idea is that you can get away with going to one stable system, but not two. In this example, the carbocation will get formed, but if we also want to make an unstable leaving group, that's just too high in energy for the whole system. So what we'll do instead is help. We'll think about making this a better leaving group by protonating it. And this is, again, one of the big ideas for the whole of the 2 semesters now. You want to make OH a better leaving group? Put a proton on it. Do a hydrogen or a proton transfer to it. Make it into this system. We have seen this when we did the acid-base chemistry. We know that these things are possible. All we have to do is add a strong acid, and that will give us this species. Now, that will be a good leaving group because of the fact that it is now going to break off and become neutral. Okay? If it breaks off, it becomes neutral, and therefore it's a very potent leaving group. That allows us to produce this carbocation, and this thing is stabilized by hyperconjugation. Okay? So we're changing the game now. We're changing the leaving group by starting with something cheaper and something easier to get hold of. So we need a mechanism for this. If we can convert the alcohol to the chloride, we need to add on to what we know. And this simply is just extrapolation. How do you know this is going to do SN1 and not SN2? It's tertiary. It is a tertiary system, so it can't do SN. This pen is not working properly today. It can't do an SN2 because it's too crowded. So what it's going to do instead is an SN1. So there are some clues here and some logic and some things that you should recognize from your past. What is this thing? What is this stuff? Acid, HCl. What do acids tend to do to other molecules? Protonate them, right? So that's just simple. That's just logical. They're going to protonate. So if we're going to protonate, we're going to end up with this, which is the conjugate acid at the bottom. That conjugate acid now is going to undergo an SN1 process by breaking off. Okay? If it breaks off, it's going to give us the carbocation. So now I have 3 steps. I protonate, I lose that leaving group, and then I produce my carbocation. What does the carbocation need most of all? Electrons. And what's floating around here that could help? Cl minus. So the last step is very much like the SN1s that we've already done. The chloride nucleophile comes in, and away we go. We get a product. But now I have 3 steps. So necessarily it gets more complicated in terms of drawing a reaction profile. Which do you think is the slowest of those 3? The loss of the leaving group. Yeah, the loss of the leaving group to give the carbocation. So this won't be as simple as the last one we saw where we just had 2 steps. This will have 3 steps. And obviously we're building more and more steps into this system. So we can do this in the opposite sense. And this is something you should think about as you're doing lab work. There are some problems in the lab where you've just got to be on your toes. You've got to read the instructions before you get to lab and then follow the instructions when you're there. You'll make something like this in the near future in the lab. An organic alkyl halide which is tertiary. And the problem with these tertiary alkyl halides is that that's a really good leaving group. So if you're not careful and you're sloppy, and you let your mixture sit with water for a while by not separating the water or not following the instructions, you'll go back to square one. You just spent the entire 3 hours doing this, taking the alcohol to the alkyl chloride. That's what you want. But if you're sloppy and you're not up on your procedures, you'll go in this direction instead. And you'll end up with what you started with, and that's just pointless. So the idea now is that this is a good leaving group, this is a nucleophile, and it will give you the opposite product. So you've got to be careful. Now, how does that happen? The mechanisms are going to come thick and fast now because they are the same thing, but just tiny little details added to them. This is SN1. How do you know it's SN1? It's tertiary. If it's tertiary, it can't do SN2. So the only thing you've learned so far is the opposite one, which is the SN1. This thing will break off as a leaving group. You'll see in a second that this is facilitated by this solvent, which is going to allow it to hydrogen bond and help the leaving group break off. That gives me a carbocation. Do you think that carbocation will rearrange? Why not? Put a logo. It's already tertiary. It's as good as it's going to get. So it's not going to rearrange. What it needs is some help. In this system, we have the solvent. And then if you follow this carefully, and this is the detail that is really important. If you trap that electrophile with that nucleophile, you produce this thing. You don't get the alcohol directly. You get the protonated version. So you have to get rid of that proton. And where that proton goes is to the solvent. If you're looking at chapter 6 and you're looking at all those little steps, the nucleophilic attack, the leaving group breaking off, the proton transfers, it's all in there. There are no rearrangements here yet, but these are all the basic same steps. So in this last step, a proton is being taken off by the solvent to give us the neutral product. That can be very confusing if you're not looking at this stuff yet, because it's all starting to look very busy, but it's the same idea. If you want to neutralize that product, you need a base. The base is the solvent, and it takes it off to give you the product. Everybody okay? You say so. We'll find out next week on Monday. So in terms of versatility, this becomes very useful because all of a sudden we can mix and match our pieces. All we've done on this slide is go from water as the nucleophile to methanol as the nucleophile. And that methanol now is going to be able to replace the chloride on the same chloride. Now I haven't changed the starter material here, so that should give you the same outcome. It's a tertiary system with a leaving group attached. They're the clues you're looking for this to be an SN1 reaction. So what's the slow step in an SN1 reaction? Leaving group breaking off to form the carbocation. Do I need to help that chloride out? Do I need to put anything on it to make it a better leaving group? Or is it good enough as it is? It's good enough as it is, so I don't need that preliminary step. I needed a preliminary step with the hydroxide because that's a lousy leaving group on its own. What will happen now is that this thing will break off and we'll produce the carbocation. But we are now in an alcohol solvent, and if we choose that instead of water, and that traps, and we get over here, this can also serve as a base, and people will say, well, okay, you've just used one molecule of this here, and now you're using a molecule of the same stuff over there. How's that possible? Well, the answer is it's the solvent. And you haven't done much in terms of synthesis yet, but when you mix molecule A and molecule B as the reagents, and you dissolve them in a solvent, the solvent is usually there in a great excess compared to what you put in there. So you have lots of solvent molecules to allow you to do this. In the last step, a second molecule of the alcohol comes in, and it grabs a hold of the proton from here, and you end up with that. And that is an ether. So all of a sudden, you've got access to different functional groups by doing the same reaction. And at the end of chapter 7, there will be a chart that says you can go here, here, and here, which will look very confusing if you haven't started looking at this stuff yet. Now, I'm not in any hurry. I can get through 7 today. I can get through 7 on Monday. Ashley. You will see it coming up in a second. Yeah, right there. Okay? Now, we are looking for clues. This is all about clues. If you want to memorize this stuff, good luck. Yes? Very good luck. Buy yourself some Tylenol. Take the weekend off. Good luck to you. If you want to know this and learn it, it's much more fun, much easier. So what we've done so far is say that halides can be good leaving groups, and also OH if you protonate it. We've expanded the sort of playing field for leaving groups. Well, the reactions we've done so far today involve proton transfer, they involve leaving groups breaking off, and they involve nucleophilic attack. We haven't mentioned rearrangements yet, and of course they will happen. So look at this system. Maybe on an exam, you are given this starter material, and you are given this product. And your job is to tell me how it happened, is to come up with the process for how that happened. So what's the clue? What do you think, if you look at this system, what tells you, when you look at the product, that there was a rearrangement? Chlorine's in a different place. That's all there is to it. The chlorine is now in a different place. So that can only happen with a rearrangement. Rearrangements require what type of intermediate? Carbocation. SN2s don't do rearrangements. You might write that down. SN2s don't rearrange. Oh, look at this. Wow. Clues. SN2s don't do rearrangements. SN1s do because a carbocation gets formed. And guess what? To do a carbocation rearrangement, you need a carbocation. It's that simple. So what's going to happen now in the presence of maybe a decent solvent with some nucleophile around? We're going to use NaCl here. This thing is going to break off. Now, what's the problem here? What type of starter material is this? Is it on the top left? Is it primary? Is it secondary? Is it tertiary? It's secondary. So it may be not as good as the others that could come off. There we go. If it does come off under the right conditions, it gives you a secondary cation. And that secondary cation has the possibility here of rearranging to become something better. Now, why not just move a hydrogen? If I move a hydrogen from over this side, on the left, would that help me at all? No. What type of cation would I get? Primary. That's horrible. That's counterintuitive because you go in the wrong direction. So what we'll take is one of these alkyl groups, move it across, and end up with a tertiary cation. That's much better. Much, much better. And then we have the opportunity for nucleophilic attack to finish the reaction off. Now you can make this reaction more complicated very easily. If I were to take, and this is an old exam question I think that's on one of my exams, if I put a wedge there, what's that trying to show you? It's chiral. It is a chiral system. And if you measure its alpha D, it will have some number, because it's not 0. And it's not racemic, it's not meso, it's chiral. If you do this and you get the carbocation and it rearranges, you trap with the chloride and you go here. What will the alpha D be for that product? Look at it. What will the alpha D be for that product? Anybody? There is enough information. Some number such as what? Look at that product. Is it chiral or not? No. So what's alpha D? 0. Yeah? Not because it's racemic, but because it's symmetrical. And again, I'm looking forward to grading this exam because I love my weekends where I spend 36 hours doing this and nothing else. But I'd love to come back on the Monday afterwards and give exams back smiling and not grumbling that people don't know this stuff because they're too lazy to bother studying it. Right? So it's up to you to get it done and organize these things so that they're okay. Right, reaction profiles. Slow step or fast step? Slow. In this example, it's a rearrangement. Slow or fast? Why is it fast? It's intramolecular, it's in the same system. And then this guy here is now tertiary, but it's not crowded anymore, right? Because it's flat. And then the nucleophile comes in. Is that fast or slow? Fast. So we can start building reaction profiles even on things that you haven't seen. You should be able to, by next Friday, draw me a reaction profile for that, having never seen that before. All right? And that will be a test. Reactions you haven't seen, but you should be able to work out. So again, let's look at this. Let's do this with a slightly different system. This is more complicated because the hydroxyl needs some help. So the first step for this process is to protonate. Where do I get my proton from? I put some acid in there. In this case, I have acid and methanol. Methanol will be the solvent. I add a little bit of acid. So we can protonate this hydroxyl, make it into a good leaving group. If it breaks off, it becomes a secondary cation. Not great. But then it can rearrange and become a tertiary cation, much better, flat. And then if we trap this thing, we get the protonated species here, which then gets deprotonated, and we end up with this product. How many steps in that process? 5. We've gone very quickly from 1 with the SN2 to 2 with the simple SN1s to 5, which is the sort of pinnacle at this point in the game. Next semester, 10, 15, 20 steps for those who are left. In this system now, we have everything going on. We have proton transfers, we have leaving groups breaking off, we have nucleophiles attacking, we have rearrangements. It's all there. So watch out for that type of stuff. If you can do that, you're in great shape. You need to be able to see these things. So if we think about a reaction profile for that, it's complicated, right? It's going to be quite complicated. And we can start off trying to predict that reaction profile, as we did in office hours this week, as we will in recitation next week, by thinking about what type of steps are involved. So in the first step, I have a proton transfer. Is that fast or slow? Fast. It's an acid-base reaction. They're always fast. After that, I have a leaving group breaking off. Is that fast or slow? Slow. If I have a carbocation rearrangement, fast or slow? If I have a nucleophile attacking a flat thing, fast. And if I have an acid-base deprotonation proton transfer, fast. Those little pieces of information there help you build your reaction profile. So you can start to do this from scratch. And again, I advise you not to memorize everything, but to actually understand it so you can extrapolate to new stuff. That's the goal here. This is the same reaction, using the reaction profile or predicting the reaction profile. We start off with an alcohol. That alcohol gets protonated. We get to here. Okay? That is activated now to be a good leaving group. That leaving group can break off and become a good carbocation. That carbocation then can rearrange. And look where I went from. I did an acid-base reaction to activate this thing. This thing is now more reactive because it's protonated, and that OH2 group can break off. That's going to give me this species here. That thing then breaks off and gives me a carbocation. Why is the carbocation in a valley and not at the top of a hill? It's a real thing. It's an intermediate, not a transition state. And you ought to be able to draw me all the transition states at the top of these hills. I'm not going to show you these things. This is up to you to learn how to do it. Okay, do your homework, practice some problems, ask some questions. Do it, or else you won't be able to do the exam. Think about carbocation rearrangement. Fast or slow? What do we say? Fast. So look at the barrier here. The barrier to the secondary going to the tertiary cation is actually quite low. It's a fast process because everything's already there and you can rearrange in the same system. Now, nucleophilic attack, not a very high barrier because the carbocation now is flat, and that gives us the protonated species at the end, which just has to get rid of that proton, and we're done. That is probably as complicated as it will get for the exam, but that is nowhere near as complicated as it needs to be for the rest of the 2 terms. Just FYI. Anybody? Anna Maria? No? Okay, everything good? Okay. So, we're starting to set up an expansion of what you can do with these systems. The SN1 reaction is not just simply a tertiary alkyl halide giving an alcohol product. It's a vastly useful, vastly applicable reaction. And we can start thinking about alcohol starter materials in a different sense. We can go back a little bit and talk about the other extreme. How do you know this won't do an SN1? How do you know that's not going to do SN1? It's a methyl group, right? What's it lacking if the carbocation formed? It hasn't got any friends. It's friendless. Okay? So there's no help from next door because there's nothing next door. So you cannot form a carbocation with this. If it does a substitution process, what must it have to go through? If it can't form a carbocation, what's the other option? It does the SN2. Thank you, Joe. Okay? So this is going to do an SN2 instead because the carbocation just isn't going to happen. Neither is my pen. All right. So what we've got here is the alcohol. Is the alcohol a good leaving group or a poor leaving group? Poor. I need to give it some help. The simplest way to do this is to add some acid. If I add some acid here, sulfuric acid, for example, it will protonate this thing. You will do this in the next few weeks in the lab. Sulfuric acid, dangerous or not? Yes. When you start doing these experiments for real, assume, and you won't be too far off, assume that everybody else in the lab is a complete idiot. And that when you're mixing these chemicals and messing with these chemicals, be aware of everybody else's idiocy. And you will stay safe. Right? We don't have accidents in this lab if we're careful. So you're going to mix something like sulfuric acid with some salt and hydroxyl, and the alcohol. And what's going to be the first step if you mix an acid with an OH group? Protonate, and you make this into OH2+. But it can't break off because it's going to give you a terrible cation. So what it can do instead is an SN2. So in this case, it won't work with just NaCl. If you just add NaCl, it doesn't work because you cannot protonate the OH group with NaCl. You need that acid to be in there. And then if you start measuring adding more nucleophile, adding more electrophile, it's bimolecular. It gets faster in both instances. So this tells you it's different. It tells you it's an SN2 reaction. In this instance, we start off with the alcohol. The mechanism then is an acid-base reaction. If you understood the acid-base reactions, you did well on that last page of that last exam, this shouldn't be too much trouble. If you didn't, this won't work. We're going to get an acid-base reaction in that first step. And we're going to end up with a train going by. Rob, do us a favor, mate, and close that door. Thank you. What's the point of doing this? Why did we put that proton on that OH group? To make it a better leaving group. But then you've got to make a concerned decision, a decision based on what you know. Does it break off first, or does it get pushed off? Pushed off. Why? Because it's a simple system, it's a methyl system, it's not able to give you a carbocation. There's a big decision to make. So now we have the leaving group breaking off, and we produce, in this case, as the nucleophile comes in. So is this bimolecular or is this unimolecular in this last step? Bimolecular. Is this bimolecular in the first step or unimolecular? Bimolecular. Could you draw me transition states for this process happening and for this process happening? Yes, I hope so. It's very straightforward once you understand what the transition state is trying to show you. How many hills in that reaction profile? 2. Which one is going to be slower, you think? The protonation step in the first step or the nucleophilic attack? Nucleophilic attack. Having said that, go home. You should be able to draw the reaction profile, even if I don't show it to you. So let's think about other systems. There are some instances where you can react alcohols with iodides. For example, iodides are great leaving groups. So all that's happening here in this system is that we're deciding whether it's SN1 or SN2. Which one is it? Why isn't it SN1? It doesn't have any friends. Okay, that's a primary system, not enough friends around to help out. So I can't break the leaving group off first. I have to do an intermolecular process where I kick the leaving group out. And in this case, my leaving group might be an alcohol. If we do this, we produce this, and that's got a proton left over, which has to come off. So in this case, we might use a lot of this, what we'll call an excess of the reagent. And so we have some around to take a proton away and to give you the neutral product. So what type of functional group is that at the end? Ether. I'm glad somebody remembers it. Good. It's an ether. So now we have an ether synthesis by simply mixing an alcohol with an alkyl halide. If you are sitting there thinking, this is way too much for me, I can't handle this, then, good luck. But if you're sitting there thinking, there must be a straightforward way to do this because 70% of the class get through. I want to be in that 70% of the class. Then that's where we come in to help you. Tyler has got SI next week, I've got office hours. We can point out the similarities and the differences and some very simple criteria for you to use to decide what's going to happen. Because what happens on this next exam way too much is people guess. It's an SN1, they guess it's an SN2, they give me a beautiful answer for an SN2. Wrong. It's an SN1. If you can't make that first decision, this doesn't work. Okay. This one is different. This one is something you haven't seen yet. This is second semester stuff, but it should be, as you get better at this, achievable. And I'll use this as an example to go back and just reiterate what you should be thinking about for mechanism. You need to do jobs. You need to do certain things in a system to convert it to the products. First of all, you need to know what those products are. So in this example, if I gave you something like this, I would give you the product because you haven't seen it before. And once you've got that product, you can start to decide what you need to do. So how many oxygens in my starter material? 1. How many oxygens in my product? 2. What do I have to do to an oxygen here? One of those oxygens must come into the molecule, right? I must introduce a molecule or introduce it to the molecule. So we can see here that one of these oxygens is retained. It's here. And maybe this other hydroxyl here came from H2O. So how do we do this? What is this? It's an acid. Good, right? That's an acid. Is there anything in this molecule that I can protonate? Why are we shaking our heads? What do you need to be a base? What do you need to protonate? A lone pair. Does this molecule have any lone pairs? Yes, it does. Okay? So the first step in this might well be protonation. And that protonation is on oxygen. And why do you think we protonate oxygen? To make it a better leaving group. It's consistent. If I do so, I'm allowing this, not necessarily in this molecule to leave, because it's bonded twice. If it was bonded once, it would leave and it would be gone. But it's bonded twice. So if one bond breaks, it's acting like a leaving group, but it's still in that product. How do I know this is SN2? Anybody? It's a primary type system. It doesn't have any friends. It's a primary type system. So that will give me the protonated product. And if I know what the product is, I need now just to get rid of one H, one proton, and I'm done. So in terms of the logic here and the sort of steps, proton transfer to set it up, what was the point of that? What was the point of protonating in the first place? To make oxygen better at accepting electrons. Nucleophilic attack. How do I know it's nucleophilic? Well, that's what we're studying. And this is capable of being a nucleophile because it's got lone pairs attached. Why should it attack this carbon? What can you put on that carbon? A little indicator of why a lone pair should want to go there. Partially positive, absolutely, partially positive. So that's the same type of stuff, just in a different system. And we should be able to get there by next week. Okay. What is left in this chapter is how do you sort of take out all the mystery? What do you need to know to be able to do this properly and be accurate and to make a decision, an informed decision on what type of system will happen and what type of reaction will happen? So this is a general sort of idea. You're going to see problems on exams, on quizzes, in which you have some substrate, some starter material. And that starter material might have a good leaving group. So far, a good leaving group is a halide. Or it might have a hydroxyl, and you have to make it a better leaving group by protonating it. And you will have some source of nucleophile, and nucleophiles have to have a lone pair. That's what you're looking for. If you have a salt, typically the nucleophile is the anion of the salt. That's pretty straightforward. And you also need a solvent for this to work. It's the swimming pool idea. You dive into an empty swimming pool, you go to the hospital. If you dive into a full swimming pool, which is full of solvent, you can swim around. It's fun. And then if that works and you mix them all together appropriately, and you set the experiment up right, you get products. And those products are isolated. Now, don't forget, you can't tell what the mechanism is unless you know what the products are. So you isolate those products, you work out what their structures are, and then you can work backwards. You can do some experiments like the kinetics, add more nucleophile, add more electrophile, see if the rate changes, and that informs you about the rate determining step. So in this case, you are looking for these ideas. You're looking for the substrate structure. All that means in English is it methyl, primary, secondary, or tertiary. If it's tertiary, what are we going to do? SN1. If it's primary, what are we going to do? SN2. If it's methyl, what are you going to do? SN2. Secondary, that's where we need to go. The leaving group type. Is it a good enough leaving group on its own? By that I mean, is it a halide? Is it chloride, bromide, or iodide? They're fine coming off on their own. They don't really need any help. What's a leaving group that doesn't do that? What needs some help? OH. The nucleophile type, this is what we're going to do now. Is it a strong nucleophile? Is it a weak nucleophile? A strong nucleophile will do an SN2. Right? It's a strong nucleophile, meaning it's reactive, it's unstable. It will do an SN2 because that's aggressive and it wants to go after that carbon and become neutral. If it's a weak nucleophile, it might allow for the SN1 to happen because the SN1 needs more time because you're forming a carbocation. We'll see that. And then the solvent here is going to be important because of the fact that the solvents can help with an SN2 or cause an SN2 to go slower, and the same with an SN1. You need to be very detailed with the approach here. So let's get started. There is, have you done TLC this week? Yes, this is not a TLC, right? It's a graph showing you that there is a correlation. SN2 favors the primary systems and not the tertiary, and in the middle you got the secondaries. SN1 favors the tertiaries and not the primaries, and in the middle you got the secondaries. The secondaries are the problem. That's the issue here. The secondaries will be the problem because they can go both directions. So here we go. General statements. Methyl and simple primary systems always do SN2. That's a given. Tertiary systems always do SN1. That's a given. But you need to know why as well. At the top, they're accessible to do SN2. Second line, they're not accessible, but they can give you a good carbocation because they can stabilize by hyperconjugation. Secondary systems can do either, which is the big problem here. So let's look at some special systems. Let's start to deconvolute this stuff and make it manageable so that we're okay for next week. This is a system called allylic. We dealt with this when we did resonance. When you have double bond and some charge here, that was the allylic cation or the allylic anion from a while ago. If you put a halide here, that's the allylic halide. Now, these systems look like what? Are they primary, secondary, or tertiary? Primary. But be very careful here. These are the type of primary systems that could do an SN1. Right? This is obviously something different. There's something extra here to help this out to do an SN1. If you put a positive charge on that carbon, even though it's primary, why is that okay? Resonance, and resonance beats hyperconjugation. If you put a positive charge on this carbon over here, lots of resonance. So that carbocation isn't as bad as a primary cation because it gets help from resonance. So do you expect these to go faster in SN1 or slower in SN1 than, say, a simple primary system? Faster. Faster because the carbocation is easier to get to. So we've got to worry about the shapes of these things. We've got to worry about what these form. If that halide breaks off in a rate determining step, which it can, you get this. Go back and look at resonance. That will delocalize. If you break this guy off and you produce the benzylic carbocation, which you'll see a lot of next semester, positive charge there, that is resonance stabilized. Okay? So if those double bonds aren't there, can I do SN1? No. Right? That's the only reason you can do SN1, because you can delocalize. Watch out for that one. Now, a bunch of tables. I find tables boring, but we have to deal with them. And some of this is intuitive. If you understand the acid-base stuff, this should not be a problem. We're going to find that some nucleophiles can be described as strong, some of them as weak, some of them in the middle. John! Dude! Did I scare you? Save it for Halloween. Strong nucleophiles tend to be negative things. They tend to be things that can share charge with other things. So I minus. Yes, it's stabilized because it's big in an acid-base sense, but it's also very polarizable in the sense that the electrons we're talking about are far away from the nucleus and they're not held very tightly. So it's actually quite easy for I minus to share its electrons with something else. Br minus likewise, Cl minus likewise, right? They're able to share their charge someplace else, which means it can be a nucleophile. Sh minus, very good. OH minus, very good. And you should be able to see why this is such a good nucleophile because of the fact that it's a very strong base. It's doing very similar thing. OR minus, very strong, Cn minus. Essentially anything that's negative apart from fluorine so far will be a decent nucleophile. So when you see next week the beginning of this on an exam, sodium NaN3, it's the N3 that's the nucleophile. NaCN, it's the Cn that's the nucleophile. It's the negative species that you're looking to be the nucleophile. Now, again, don't memorize this. It will come with practice. But can you tell me why this is a weak nucleophile, but this is a strong nucleophile? Go on. That's it. That's it. H2O is neutral, it's stable, it's not in a hurry to do anything. Hydroxide is in a hurry to do stuff because it's unstable. It's more reactive and therefore it should be a better nucleophile. So we'll see that manifest itself in a second. You can do SN2 reactions with hydroxide. You can do SN1 reactions with water. Simply because the hydroxide is in a hurry and the SN2 is all about the nucleophile going after something in a hurry. Hydroxide will do that. Water, yeah, it's water. It's stable. It'll wait for other things to happen, such as a carbocation being formed. Actually. Because H2, you think about where S is in the periodic table, it's below water. You compare this with this, and this is what I'm doing on this table, just comparing some of them. Water's more electronegative, or so the oxygen is more electronegative, holds on to its lone pair tighter, it's harder to give away. A nucleophile has to give that lone pair away. Sulfur's less electronegative, holding on to those electrons less tightly, it's easier to give those electrons away, therefore it's a better nucleophile. Okay, so these are simple things that, in their own little sort of compartment, they're not so bad, but put it all together, it gets a bit hairy. Have a look at that table, think about why we're categorizing them that way, and let's start doing some chemistry. What we're trying to learn here between now and the end of Monday is how do you know which reaction happens, especially with the secondary systems. Now with this example here, it should be fairly obvious. Why is this going to do an SN1? It's tertiary, that's all you need to worry about. And that slow step gives you the carbocation. The leaving group here is what you need to be concerned about. If I have a halogen, other than fluorine, it should be able to break off on its own. If I have a OH group, it needs some help. I need to protonate it. And then this is a general statement that you should be aware of. Weak bases make good leaving groups. Things that have strong conjugate acids are weak bases such as I-, Cl-, Br-, H2O. They're all good leaving groups because of that. So the detail here goes back to understanding pKa's. Understanding, bring that stuff with you. I know people are forgetting this stuff because it was 4 weeks ago. You cannot do this and hope to get through this class. If you took a Japanese class and you forgot all the words you learned in the first couple of weeks, you wouldn't pass that Japanese class, right? I would hope not. So it's the same here. Don't forget the language from earlier. We need to use it. There's your pKa table. We think about strong acids having weak conjugate bases, exactly there. So I- is a very good leaving group because it can accept a charge. Why is I- good at accepting a charge? Because it's big and it can spread that charge out. Why do you think this negative charge here, if I put a negative charge right there, why should that be good at accepting that negative charge? It's got resonance possibilities, it can delocalize that charge, absolutely. Those same ideas from acid-base chemistry now come into what defines a decent leaving group. So again, that table you've seen before. We're just trying now to relate it to something you've seen. So I'm going to finish off today with this idea, and then we'll come back on Monday and finish this chapter off. There's not a huge amount left, just a bit of solvent stuff, and then we'll get into 8 for a little bit. I-, very good leaving group, doesn't need any help. In reality, not much fun to work with because they're so labile. You put the iodides in the light, you put them in the sun for a while, they break apart because it's a weak bond. Bromides are a good compromise because they don't do that and they're shelf stable. You can keep them in the fridge or on the shelf and they're fine. Chlorides, not as good leaving group because they're not as big, but they will work. Now these guys on the right, these are sort of modified, invented leaving groups that if these don't come off, your leaving group isn't coming off. Okay, so these are the best of the lot. We have something called a tosylate, which you will know, you'll need to learn. And it's based on a molecule called tosyl chloride, which is this guy. And the benzene ring plays no role whatsoever. The methyl group plays no role whatsoever. The history behind this is simply that stuff is cheap. It is a byproduct from a pharmaceutical synthesis that is made in large scale. Rather than throw it away, they turn it into that chloride. We buy it for way too much money, and then we can use it as a leaving group. So we can take an alcohol, and instead of treating it with an acid, the problem is, get this out of the way now, much of what we are to do in the future, starting on Tuesday or Monday of next week, is that we've spent a lot of time over here. We've spent a lot of time on this end of the molecule doing expensive stuff. There's a lot more over there, big cycles, double bonds, alkynes, all sorts, in a pharmaceutical type synthesis. And we've spent a lot of time doing that. But if we throw acid into this molecule, it all goes to crap, right? because over here reacts with acid. But we want this to react with acid to make it a better leaving group. So how do you do that? How do you get around that problem? Well, you invent something that doesn't involve an acid to do the same job. And that's where this tosyl group comes in. We take tosyl chloride. For now, this basically comes in, attacks the sulfur, kicks out the chlorine. That will do for now. You make what's called a tosylate. There's the word right there. That tosylate is a much better leaving group than OH, and it's probably as good as an iodide. But we don't have to worry about iodides being unstable, and we don't have to worry about adding acids to hydroxyls. Now, what will happen? Where's the nucleophile down here? Which part is the nucleophile? N3 minus, right? That's got negative charge. It has to come in here, attack from the back, and it will kick this out. Why should that be such a good leaving group? Look what you get. Resonance stabilization right over there. This one is an example of just a modification of that. You don't need the benzene ring. It's a small methyl group. It's a liquid. It's not as easy to work with, but it can be done. The mesylate has about the same leaving group ability as this. To finish off today, and I'll start with this slide on Monday. Why should putting a CF3 group on there make this the Rolls-Royce of leaving groups? Who said that? Oh, I'm going to go home happy. The dog won't get kicked. Excellent. Oh, we haven't talked about that yet, have we? And your motivation to do well on my next test? Yes, okay, we'll do that on Monday. But absolutely, induction. That helps stabilize the negative charge on top of the resonance. I bid you a good weekend. Study like crazy.